So if I have my solid sphere there that is rotating about, I guess I do need to state one other thing. That's the formula if it's rotating about a central axis here. So if I have a solid sphere rotating about central axis, and the mass is 3 kilograms and radius is 0.5 meters, the moment of inertia is just a straight up plug and chug, 2/5 times the mass times the radius squared. And doing fancy math here, let's see, so that's basically so 0.3 units.
Oh, is this the kilogram meters per second, or was that something else?
That's momentum.
Looks like kilogram meter squared.
It is kilogram meter squared. There is no nice one word unit.
What was the picture that you erased was asking us
The picture that I erased?
yeah, the L.
The beam.
Oh, that was using that as a starting point for coming up with the moment of inertia here. So it was just a rod rotating about the end. What was the kinetic energy of that rod?
So I have back couple classes ago, impulse equals force times change in time. So would that not apply in any way in this situation?
No.
What would that formula be used for?
Force times change in time. So impulse is equal to the change in momentum or equal to force times time.
Mm-hmm.
That would deal with chapter
Chapter
8.
Is this impulse the same impulse, or is this a different concept?
Oh. I guess the eye's messing you up.
Yeah, so it's different.
Impulse vector, that I is not a vector, that is the moment of inertia.
Oh, okay.
Yeah, sorry.
Gotcha.
Let's make that explicit. Moment of inertia.
Gotcha.
Some textbooks will call it rotational inertia. I typically do not, but if you see rotational inertia, that is the same thing as this.
Okay.
Okay, sorry about that. And also to avoid confusion, some textbooks, instead of using vector I here, will use a vector with a capital J for impulse. Right. Now notice how fast it was spinning has absolutely nothing to do with the moment of inertia here. In terms of, I've done these with this group, right? Okay. So again, moment of inertia is an indication of how easy is it to change its movement once it starts rotating. Similar to mass in linear motion. All right, so we've got a mathematical thing here, sort of description of it. We're gonna get to a conceptual one. One other math piece I need to do is, well, let's just do it in terms of this. If my axis of rotation is the center of me, think about what is my moment of inertia like this versus moment of inertia like this. Which one would have a greater moment of inertia?
With your arms in,
Why?
you spin faster when your arms are in.
What does that have to do with the moment of inertia? Moment of inertia, there's how fast you're spinning is not in the formula whatsoever.
Gotcha.
The radius So your center would be larger with your hands out.
Therefore,
The moment of inertia would be larger if your hands are.
yes. And you just spin faster because there's a inverse relationship there. When moment of inertia drops, the rotational velocity would increase.
Okay,
So conservation of angular momentum.
okay.
Not there yet, but that's coming up. All right, so now, the rod over there. We're gonna get rid of this. So a rod rotating about its end, the moment of inertia formula is pretty sure it's 1/3. Yeah, 1/3 ml squared, where L is the length. But if I take that same rod and I rotate it about the center, so rotate it, spin it around like this as opposed to like that, my moment of inertia formula is 1/12 ml squared. For reasoning, sort of Jacob sort of outlined just then, is that if my axis of rotation is here, I have more mass that is farther away. And looking at the formula that I will rewrite, R is a more dominant factor because I'm squaring it. R affects it much more.
Would the mass on both ends also have something to do with that? Like, say you've got that specific rod, but you've just shortened it, but you're still spinning it on the same axis, for the top part.
Okay.
Wouldn't that be somewhat similar to the moment of inertia on the bottom one? Or would it be different because the bottom one has mass on both sides of the axis of rotation?
If you wanted to relate the two, matter of fact, we can derive this from that, sort of unofficially.
Okay,
If I treat this as two rods
yeah,
rotating about the center, or rotating about their endpoints. So if I just look at one of them rotating about, the length is half of what the length was. The mass is half of what it was. So I could treat the moment of inertia of this half bar, so this is length L and mass M, this is mass M over 2 and length L over 2.
okay,
So the moment of inertia of just that half piece would be 1/3 M over 2 L over 2 squared, which is 1/3 times 1/2 times 1/4 ml squared, which is 1/24 ml squared. But I
okay,
got two of them,
yeah,
because ultimately I'm just adding up. This is just a giant sum. So if I've already got a formula for that based on this, and I got a formula here. So therefore I've got two of them. So the moment of inertia of the whole thing would end up being 1/12 ml squared.
okay.
Yeah, so this is kind of just to like, go over what we just did, so, on the left, you have I equals 2/5 mr squared, but then, like, so when would we use each equation, basically, and like, how would that, like, why is the fraction changing? Is what I'm wondering.
So anyone want to speculate?
Which fraction is he asking about?
So
I think the
you
2/5 over there, the 1/3 here, the 1/12 here.
Well, that's a sphere.
Yeah, I guess it's based on the distribution of mass in the solid.
Yep.
So are we gonna be giving the fraction, or are we expected to like know what it would be based on?
That'd be cool if you know them, but no, they'll be given to you.
Okay.
Just for reference, how would we know? Is it based off of, just pure memorization, or is it some kind of factor that goes into it?
Calculus. I mean, you can go through and derive each of these.
Okay.
Or it is possible to. If you haven't had calculus, it becomes very difficult.
Okay.
So basically, all we have to basically worry about is, finding the, using the mass and the radius to find, or radius or length to find the I.
In terms of, the way I heard you word that, and maybe I misheard. At this point, yes, I'd have to give you the mass and the length and you'd be able to figure it out. The fraction depends upon the shape and where the axis of rotation is. So for example, here, it's the same shape, but different axis of rotation, and so therefore the fraction is different, 1/3, 1/12. Yeah, I forgot where I was going with that one after that. Do you want to ask your question again, or was it potentially answered?
I mean, I think I'm good now.
Good.
Yeah.
There's a different way of actually deriving this from this, or deriving this from that. And I want to go into it. I'm not going to derive the formula, but I am going to present it, known as the parallel axis theorem. I think in some of the video titles I labeled as PAT. Because the farther out mass is, the larger the moment of inertia. Parallel axis theorem is based upon the moment of inertia if the axis of rotation is at the center of mass. So for example, in this rod right here, if the axis of rotation is there at the center of mass, that's basically going to be the smallest moment of inertia I'm going to get for that rod. Because if I start moving the center of mass away, then suddenly I get mass that is farther distance from it than the axis than it was before. So right there, the endpoints are equidistant. If I move the axis over here, that suddenly has an exaggerated effect because I now have mass that is farther away. Now, how much I move the axis also affects the amount of the moment of inertia. And so, times the mass, times the distance that you actually move it, squared. So the moment of inertia about some point, or some axis, is just the moment of inertia about the center of mass plus the mass times h, where h is distance from center of mass to new axis. So in our case over there, about the center, 1/12 ml squared. That's the moment of inertia about the center, of the axis about the center of mass. If I shift it off to the outside here, I'm shifting it a distance half the length, so that's 1/2 L. And so the moment of inertia about this point would be the moment of inertia about the center of mass, so 1/12 ml squared, plus the mass times how far I shifted it squared, 1/2 L squared. So I end up with 1/12 ml squared plus 1/4 ml squared. And so I got a twelfth of an ml squared there, a quarter of an ml squared there, and so 1/12 plus 1/4 is 1/3. I have a disk here. Mass is, 2 kilograms, radius is 0.7 meters. And I don't care what the thickness is. And I have a rod here stuck into the end of it, or super glued to the end of it right here. The rod's not going all the way through to the center. This length right here, we'll just say 0.8 meters, and the mass is 3 kilograms. The moment of inertia of this disc with rod sticking in it. So in essence, this is the scenario here, something like that. And it's going to rotate about the very center. What is the moment of inertia of this combination?
So the sphere is, or wait, that's a sphere. The disk, is the one for a disk the same as a sphere?
It is not. Disk, 1/2 mr squared,
Okay.
not the center of mass.
Plus, would you do plus the rod? Would be like,
Yeah. So you do the moment of inertia of the disk plus the moment of inertia of the rod, because again, ultimately, it's just a huge sum, and so we just happen to break up the sum and do this one part plus that part. Or if you really want to, if you just enjoy the math, you can break this up into an infinite number of pieces and add them all up, plus this into an infinite number of pieces, add them up. But it's just the sum of the two pieces. And disk, so we have 1/2 mr squared. And now the rod, sorry, Jacob, I cut you off.
the rod is, wait, was that 1/12? No, that was 1/3,
It is not 1/3
Oh.
or 1/12. Why not?
because there's more distance to the center of the disk.
Yes. So this would be the moment of inertia of this rod about the center of mass, so the 1/12 ml squared, plus the mass of the rod, let's specify, this is disk, this is rod, times the distance that the center of the axis moved from the center of mass. That's the center of mass right there. I need to know that distance.
1/2 of 0.8 and 1/2 of 0.7? Or
Yep.
no, 1/2 of 0.8 and then plus 7.
Oh, yes, thank you.
So it'd be 0.12, oh, 0.11,
1.1 meters?
1, yeah.
So this would be half the length of the rod plus the radius of the disc. Squared. So now let's plug numbers in. So I got 1/2 times mass of disc times radius squared plus 1/12 mass of rod times there times the length of the rod, 0.8 squared, plus mass of the rod times 1/2 length plus the radius, that's 1.1. I think that's what you said, squared.
Yeah.
So 0.4 plus 0.7, 1.1. And then it's calculator exercise.
I could be wrong, but I have 4.28.
Yeah. Okay. Let's finish it up.
Is it kilograms times meters squared?
Yes. This is by far the dominant piece of the whole thing. Lisa?
So when you're making the equation, before putting the actual, values in, so when you had the MR 1/2 L plus RD, like, yeah, how did you find that part?
Again, for the parallel axis theorem, when you shift the axis of rotation from the center of mass to some other spot, you're gonna tack on this plus mh squared, where h is the distance from center of mass to where the new axis is. So there's the center of mass of the rod, and I shifted it to here. That is the new axis of rotation, because it's rotating about the central spot right there.
Okay, so when you move it, like, so when you move the center axis, then you gotta add the plus mh squared,
Right,
okay, and that's what you did.
yes. So h is half the length of the rod plus the radius of the disc.
I don't see where you did that, because it's showing, I see like half L plus RD squared, but is that the same as MH squared?
Yeah, so h, yeah, this piece right here, that's h.